Hello, this is the extra lecture for the section on global tectonics, plates and plumes. And in this lecture, I would like to cover some of the details from the material in the book that may or may not be covered during class time. Remember, you are responsible for all the material that is in this lecture. The first thing I'd like to point out is that there is a lot of material in this chapter on global tectonics. And perhaps one way to organize this would be to make a table like the one on the screen that shows the different types of features that you might find along these different plate boundaries. For instance, earthquakes and faults, rock types, rock ages, heat flow, seismic tomography, and other features that are particular to the different types of boundaries. The check marks here show the areas that are pertinent for the specific boundaries. Note that for transform boundaries, the only thing the book talks about are earthquakes and faults, because that is the main characteristic of these boundaries, and also the additional material about ocean transforms is important. So one way that I would recommend going through this information is to produce this chart and populate it with some details from the book, and that'll serve you well in terms of learning this material. But there's a lot of stuff.
Let's first start talking about divergent boundaries, and in particular the age and the magnetism of the ocean floor. So here is a divergent boundary where we have the asthenosphere welling up along a boundary that is separating, moving apart, and as a result we have new ocean crust forming. So we saw this relationship or this feature in our work on discovering plate boundaries, where along certain boundaries there was very young rock, shown in the dark colors, and away from these boundaries in a symmetrical pattern the rocks got progressively older up to about 180 million years old. So actually the ocean crust is pretty young because some rocks on continents are over 3 billion years old, and the ocean crust, the oldest, is 180 million years old. So we have to explain that. We also have to explain why we have this variation in the pattern of ages in terms of being very narrow here and being very wide here. And that's a pretty cool explanation. And also notice that the symmetrical pattern over here on this side of the Nazca plate is not repeated. The pattern over here up to green is not repeated. So we need to explain that as well. So let's take a look at some age and magnetism data to help us understand. So first of all, magnetism. So the Earth has a magnetic field, and when you have a compass in your hand, it points to the north. But geologic studies have actually shown that sometimes if you had a compass during some times in geologic time, the magnetic needle will actually point to the south, and this is called reverse polarity. So there's a lot of data on this slide. Okay, so let's take a look at this. So if you went out onto the ocean floor and pulled a magnetometer behind a ship, you would find that the magnetic signatures of the different rocks changes. Some rocks have a normal polarity, that is, they have minerals when they formed indicate that that the magnetic pole is to the north, and then they have other parts of the ocean floor that have magnetic signatures in the minerals that indicate the pole was in the south. And you can see this is kind of a zebra pattern, alternating between white, which is reverse polarity, and dark, which is normal polarity. Now you can see the same type of feature on continental rocks where you have these lava flows. And this kind of produces this pattern where you have zones of normal, reverse, normal, reverse, etc. Now the cool thing is that this pattern from rocks on continents is also or consistent with the pattern that you see on the ocean floor, and these correlate very closely. And so the explanation for that is along these ridges, and this is the Gorda Ridge and the Juan de Fuca Ridge, which is off the coast of Oregon, rocks at new rocks forming at the ridges became magnetized, and as they move off, they maintain that magnetic signature. So let's take a look at a model to explain that. So here we go. So here's our divergence setting. Okay. Now the compass on the left shows a time of normal polarity. So rocks become magnetized along this boundary. Little minerals align themselves with that pole, indicating that the magnetic pole was in the north hemisphere. So the red arrows are pointing north. Now during times of reverse polarity, as shown here, the magnetic minerals indicate the pole is to the south. So we have new bands showing. Okay, so those ones moved off the divergence setting, and now we have new ones here. The pole shifts again to the north, and we have new bands. And so you can see the key here is that these symmetrical bands of the same age, these and these and these, are symmetric about the divergent setting, and the explanation is that as these rocks move away or are formed and move away, they split into these bands. Now, a couple questions arise, of course, like why do the poles shift and what's the process? And that's something that we'll cover in later lectures. So this model nicely explains the patterns that we saw in discovering plate boundaries. New rocks form along the divergence boundaries, okay, and during the divergent movement, they break and move apart and form these nice parallel bands. So the explanation for why this is so narrow and this is so wide is relatively straightforward. It's just that this ridge is spreading a lot faster and therefore produces more rock. But why do we lose the pattern over here and somewhat over here? Well, that explanation is also rooted in plate tectonics. Along this boundary, there's a subduction zone, and the ocean floor moves below the continent of South America. And up here, the ocean floor is moving below the continent of North America. And so these rocks have been consumed during subducting activity. And that's why you lose that pattern over here. So that's pretty cool, and that highlights the idea that convergent boundaries are also called destructive plate boundaries, and divergent boundaries are called constructive because we're making new crust. And of course, transform boundaries, which are shown here by these chiseled part or broken part of divergent boundaries, no crust is created or consumed, and so they're called conservative boundaries. So we're going to continue to collect data to help support the idea that divergent boundaries are areas where the ocean floor or continent in some cases is spreading apart, and warm asthenosphere is moving up into that boundary and creating new ocean rocks. So let's look at a couple other pieces of data. So here is a graph, or a model, if you will, of water depth versus degrees longitude and heat flow units. Okay. So if that model is correct, you would expect that you'd have magma rising above liquid rock or mushy rock that's warm, rising above the area at the crest of the mid-ocean ridge. And when you do heat flow measurements across the oceans, you see that you do get increases in heat flow at these boundaries. So this model here is consistent with the data. Let's look at some more data. So this is another graph or another model of heat flow units. So how much heat is moving through the crust versus distance from the ridge crest. So here's the ridge crest, we're moving away. Now if we assume that cooling is occurring by conduction, that is, there's not a lot of fluid penetrating deep to cool the crust, we would get a cooling curve or a heat flow curve that looks like this. And note that here are actual measurements of heat flow, and they fall pretty close along this boundary. There's some slop here, but it's pretty close. So again, our model here is consistent, or our model here, the conduction, is consistent with observations. So we're getting some sense that there's a lot of information that supports this model of divergent boundaries. So let's keep hammering away at supporting our ideas for divergent boundaries and look at a couple other types of models. Okay, so this model here shows water depth versus age of lithosphere. Okay, so what we know is that as rocks move away from the hot area around the ridge, that they get cooler and thicker. Okay, and as a result, they sink into the asthenosphere, and therefore the water depth gets greater. So this curve shows the water depth, and here's that. This model shows this curve is a model that shows the water depth, and notice that here is information that's actually taken from water depth, and there's a very close correlation. So once again, the model of the crust getting thicker and sinking and producing greater water depth is consistent with observations. Here's another model. We're just killing this thing here. Here's age of lithosphere versus depth in the crust or in the earth. And using heat flow data, we can come up with a profile of what the crust looks like in the ocean. And our known here is the depth. We can get that from other types of information. And here is the curve from that information that shows the boundary between the lithosphere and the asthenosphere. And these results are broadly consistent with other observations. So in conclusion, we have a lot of information so far that supports the idea that the divergent boundaries have a process that involves separation of the ocean floor and development of new rocks at these boundaries. It's a pretty solid idea. One of the other models that's shown in the book is this map of the Earth that shows what we call seismic tomography. In this diagram, the red areas show areas where seismic waves travel slower, the S waves in particular, and faster, and the blue colors show where faster S waves travel. So this is a pretty complex idea, and the details are covered later in the book, but I wanted to preempt that a little bit and discuss how we come up with this actual information shown in this diagram. So this is from a chapter later in the book about motion interior of the Earth, and shows how this seismic tomography data is collected. Okay. So this starry thing here shows the location of an earthquake, and these are paths, or these are the concentric wave fronts that emanate from that earthquake. Okay, so these guys up here show a record of when those waves arrive at the different recording stations, which are shown here, here, and here. The red area shows regions of the mantle where waves travel slower than normal, and the blue where they travel faster. So these usually are attributed to warmer areas. These are attributed to colder areas. So this station here, oh, one other thing. So the triangles here show the expected earthquake arrival times. So this station here shows that the arrival time, the time that the ray path gets to the seismic station is the same as what's expected. Okay, so let's take a look at the next slide. This seismograph shows that the ground shakes and this wobbly line develops later than it is expected if it traveled through homogeneous crust, like down here. So the interpretation of that is that this wave, this part of the path, must have been slowed down slightly. And one way it gets slowed down is by traveling in a material that's a little warmer, perhaps has some melted rock that slows down these waves. And then as the wave moves, at this station the waves arrive a little earlier than expected. And once again, if this was homogeneous, like over here, it would arrive at the same time. The interpretation of this is that at this point in time, the waves have sped up a little bit because they're traveling through something that's a little colder than the surrounding material and therefore has a higher velocity. So this map then shows areas, of relatively warm areas in the mantle versus cold areas in the mantle. And it's broadly consistent with what we've determined from our other data sets. Oceanic ridges and a continental rift valley over here in Africa are warmer because the asthenosphere is welling up there, and continental areas, which are thicker and colder, are blue and therefore a little bit on the colder side. Now, this model here is developed through thousands and thousands of computer hours and manipulation of data in a very complex process, but produces this very nice graphic that once again supports our ideas about divergent boundaries. Next, I wanted to talk a little bit more detail about convergent boundaries, in particular subduction zones and the types of earthquakes that we find along these boundaries. I really want to hit the home on this. So here is a map of South America, and it shows a bunch of earthquake locations, the epicenters, and the red ones are shallow, 0 to 30 or so, and as we get up into yellows they get much deeper, greater than 500 kilometers. So that's a pretty deep earthquake. Remember from our work with discovering plate boundaries, divergent boundaries, which are a combination of divergent and transform boundaries, have relatively shallow earthquakes, all red. But notice the pattern here, red, shallow, and as we go towards the continental area, they get much deeper. Okay, so this pattern is characteristic of subduction zones. Deep earthquakes away from the plate boundary, relatively shallow ones at the plate boundary. So we need to explain that distribution. And here's a model that provides one explanation. So here are the earthquakes again. This is a cross section, distance from the trench versus depth. So here are the shallow earthquakes, which are occurring in this very cold, dense oceanic plate that's going down below South America. Here are some earthquakes that are on the South American continent. Okay, so those just occur in response to stresses. So as you can see, the earthquakes, the different depths, highlight the subducting slab that goes below South America. And if you look at other subduction zones, like in Japan, in Southeast Asia, you'll see similar features. Sometimes the subduction zones are more shallow, sometimes they're steeper, but this pattern is characteristic of subduction zones. We can also look at seismic tomography within subduction zones to see if that model of the subducting slab below the continent is a solid idea. And in this case, we're going to look at a place where ocean crust, relatively young, and older ocean crust over here meet along a convergent boundary just north of New Zealand. The question is, what should we expect to see in terms of the earthquake distribution? And another question would be, which way do you think the subduction zone would be going? Would it go that way or that way? So let's have a look. Both tomography data and the earthquake epicenters support the idea that there's a subducting slab below the volcanic arc.